Deep inside the high-voltage transformer powering your city, solid steel is physically flexing 120 times every single second. If that vibration shifts by a fraction of a millimeter, paper insulation turns to dust, sending 500,000 volts straight into flammable oil. Superheated copper bakes surrounding transformer fluid, generating explosive hydrogen gas trapped inside a sealed steel vessel. When internal pressure breaches structural limits, the outer steel seam tears open, exposing superheated oil to open air. A single core failure triggers automated breakers, dropping a multi-state power grid off the line in under 90 milliseconds. To understand why these massive machines are failing, we have to zoom down to the atomic structure of silicon steel. To stop stray electrical current from jumping sideways, a 400-ton core isn't solid iron, it's built from thousands of microscopic steel sheets. Without this laminated design, internal swirl currents, called eddy currents, would bake the iron core solid in seconds. Engineers stretch and roll this steel to align its atomic crystals in one precise direction, making magnetic travel effortless. As alternating current cycles, magnetic domains inside the steel realign, physically stretching the metal with every wave. Because the steel stretches on both positive and negative peaks, a 60 Hz grid produces a continuous 120 Hz physical vibration. Over 30 years of continuous hum, these microscopic expansions grind structural clamping bolts loose. Unclamped laminations rub together, scraping off varnish and creating direct metal-to-metal contact points. These microshorts allow stray current to jump across layers, creating localized hotspots exceeding 500 degrees. Grid operators extract oil samples monthly, using gas chromatography to detect early core breakdown before failure. When carbon buildup drops oil insulation strength below critical thresholds, a short circuit becomes inevitable. While mechanical wear weakens the transformer internally, the real catastrophe requires an external trigger from space. A solar flare hurls billions of tons of magnetized plasma across space, directly toward Earth's magnetosphere. Seeking the path of least resistance, these low-frequency direct currents flow straight up substation ground pins. When DC mixes with grid AC power, it shifts the entire operating wave off its zero axis. This DC bias forces the steel core into magnetic saturation during half of every single power cycle. Unable to carry more magnetic energy, the saturated core spills raw flux out into structural tank walls. The steel tank becomes an accidental induction heater, scorching surrounding oil within minutes. Saturated transformers consume massive reactive power, causing grid voltage levels across whole regions to collapse. Distorted magnetic fields generate dangerous harmonic frequencies that pulse down transmission lines. Automated protective relays detect the distortion, instantly disconnecting multiple substations simultaneously. Even if the grid survives the initial surge, internal copper windings are permanently warped beyond repair. You can't just replace a 400-ton transformer. Manufacturing takes up to 3 years, with zero spare inventory. Inside the transformer, gas accumulation triggers the mechanical Buchholz relay, locking the unit down completely. Moving a replacement requires specialized Schnabel railcars, custom route permits, and cleared bridge clearances. To stop solar blackouts, operators are installing neutral blocking capacitors to trap ground currents before they enter. Acoustic sensors now monitor frequency signatures, using AI models to catch microfractures months before collapse. By isolating ground pathways and reinforcing core structures, grid engineers are building a defense against cosmic events.
If you want to understand how the world actually works beneath the surface, hit subscribe.